Alright, on my last video I kind of got cut off for a minute, but what I was trying to explain was what our center of mass really is. This says that our center of mass is at 4. So if we wanted this to balance without moving the objects, we would need to move our fulcrum or our center of balance to the mark at 4. So we would need to go to 4. And then when we pulled out these silver columns, it would balance. So that's what our center of balance is. Another thing that we can look at with our center of balance, now we have to change all of these units because now this would just be 1 unit away from the center of balance. This would be 2 units away from center of balance. This would be 3. And then this would be -1, -2, and -3. So that's 3 units the opposite direction. So now to figure out what our mass is, our moments should equal each other on each side of our center of balance. That's how we know that we have the right answer. So 5 times 3 would be 15 because we would take the mass times the position, plus we have 2 masses over here, so 3 times 1, which is 3. So the total moment that we have on the right hand side is 18. Then on the left hand side, this is a mass of 6 times a position of 3. So we would have 6 times 3 over here, which is 18. And that's the only mass that we have. So now on the left hand side, we also have a moment of 18. So if your moments are the same on both sides of your center of balance, then your balance beam will balance. Okay, now the next part, the last part is if P equals 4, which we kind of already gone over this, you should kind of have an idea of what this answer is going to be, but I'm going to go through the whole equation for you. If P equals 4, then the moment about X equals P is the moment at P. So they are now saying what happens to the moment when our point, our center of balance, is changed to 4. All right, so how would we identify that? So we could go back through and find its position according to 4, the center of balance being 4, using all of these points, kind of like we just did a minute ago. But there is an equation to do that. So if you've already figured out all of this information up here, then there is that equation. So we can take the moment at P is going to equal the moment at the origin. Okay, so the moment at the origin minus the total mass times our new position P. Okay, that will give us our moment if we move that center of mass to 4. So the original moment that we had, I deleted all of my stuff here. Our original moment was at 56. Our total mass was 14 times our position of 4, because they tell us right here that P equals 4. So that is going to equal 56 minus 4 times 10, 40, 56. So 56 minus 56, which equals 0, which you should have been able to estimate or guess or know that that's what it is after all of the information that we went through about what happens when our center of mass is moved to 4. So when we end up with a moment of 0, that means that our balance or our teeter-totter, whatever it is completely balanced. And when you take your columns out, that it will stay balanced. All right, we'll go on to example number 2. All right, for example number 2, we now have 4 objects on our balance. We need to figure out what the total mass is. First of all, thought I changed that back to a lowercase m, but apparently I didn't. So this should be a lowercase m. So our total mass is equal to 7 plus 4 plus 10 plus 13. And then that is going to equal 10, 20, 34. And the moment about the origin will be the mass times the position. So 7 times 5 plus 4 times 1 plus 10 times 2 plus 13 times 4. So we'll have 35. Oh, these should be negatives. So 7 times negative 5, 4 times negative 1, 10 times positive 2, 13 times 4. Very good. So negative 35, negative 4, plus 20, plus 40, 52. Okay, and then we'll have negative 39 plus 72. And our moment about the origin, you get a final answer of 33. Alright, then the center of mass, or our x bar, is going to equal the moment over the total mass. So 33 over 34, and then the way they want you to write that answer is as a decimal with 2 digits. So 33 divided by 34 is going to end up being 0.97. So our center of mass for this is going to be at positive 0.97 position. Then if p equals 2, then the moment about x equals p is the moment of p, which is then going to equal the moment, which was 33, the moment about the origin, 33, minus the total mass. Total mass is going to be 34, times p, which in this case they are giving us p is equal to 2. So we end up with 33 minus 68, which is equal to negative 35. So what this tells me is that we now have a moment of negative 35. So this tells me that if I move my fulcrum to 2, which would be over here, erase this. Alright, so if we changed our center of balance to be at 2, this point here is now our center of balance. So say we move this yellow fulcrum to this point at 2. Does that not ever always erase for me? Okay, so if we moved that, then this 10 grams is going to be nothing. It's going to be 0 because it's going to be at a position of 0. So this 10 grams is as if it's not even there. It doesn't help me out to the left or right either. And this over here, 13 times 4, is going to be at 52, a moment of 52. Over here we'll have a moment of 4. Oh, wait, that's wrong. Oh, go back, because we're moving our fulcrum, sorry. So let's renumber these so we don't make that mistake. So this is going to be 1 unit away, 2 units away. Then this will be at negative 1, negative 2, negative 3, 4, 5, 6, and negative 7. So you can see how much heavier we're going to be on the left side, on the negative side. So when we look at all of these moments together and then look at the difference, and how they balance will be 35 moments heavier on the left-hand side. That's what that tells me if I move my fulcrum over to the right 2 units. All right, and so that's all you need to know for those first few problems. And let's go on to our next examples. All right, for example 3, we are now going to be going into 2-dimensional objects. So we're no longer just on the number line. The only difference for this, we're still going to be able to find our total mass. The only difference here is we are going to use an X bar, which is going to give us the X location. X bar is going to equal the moment in Y over the total mass. And then Y bar, or our Y position, is going to be the moment of X over the total mass. So a little different than what you would think. You would think that we would use the moment in X to find X bar, but it's the opposite of what you would think. And that's why I would suggest finding the mass in Y first, and then that's what you'll use to find your X variable. And I don't know if that'll help you not make that mistake or not, but that's the biggest concern that I have right here, making sure you remember that the moment in Y is what we use to find our X position. All right, so let's go through. You can look at these 4 objects. I've graphed them on here so you can kind of get an idea of what the weights feel like and kind of what you think. I mean, obviously, our center of balance is going to be somewhere inside of these objects, and it's most likely going to be closer to this direction, since a lot of our weight is over here. So we're going to have to be in the middle of these 2 heavier points, but yet we're also going to have to be a little further out this direction. It can't be, like if it's just these 2, we'd have a center point, but we've got more weight over here. So that's going to pull our center of mass a little bit further to this direction. So somewhere in here would be my estimation of what the center of mass would be. So let's start looking at this. We've got total mass is equal to, and I'm kind of running out of time here, so I'm going to go ahead and give you these numbers since I already have them calculated. That one is going to equal 40. And then our moment about the y-axis is going to be the mass times the y position. So 13 times 2 plus 9 times 7 plus 5 times 3. And how this works is this is giving me how far off of the x-axis it is. So now we're kind of thinking of that x-axis, we're using that as we used the origin before. How far off of the x-axis is each one of those points, which is actually our y point. So that's why we have to use that moment in y to find what the x position is. All right, keep hurrying. Negative 13 times negative 6. All right, all of that is going to equal 26. The m sub x, or our moment of x, is going to equal 13, which is the mass times the x position, which is 5, plus 9, which is the mass times the x position, which is negative 6. And again, this is how far off of the y-axis, how far away from the y-axis is each one of these positions. And that's why the moment in x is what we use to find the y position. And then all of that is going to equal negative 22. I've got to pause here and reposition my page. All right, so my final answer, I'm going to have x bar and y bar, and that is going to be given by 26 over 40, and y bar is going to equal negative 22 over 40. And so my final answer is 0.65 times negative 0.55. And then I wanted you to look and see what that looks like. So 0.65, negative 5.5, our center of mass is going to be right in here. And so if we wanted to balance all of these 4 objects together on one mat, on one plate, then that is where our center of mass would be.